Hi, I'm Jim Burnham, and this is our speed review through Unit 2. Unit 2 is covering molecular and ionic compound structures and properties, and this covers between 7 and 9% of the average AP exam. So here's the long, drawn-out explanation. You're welcome to read that. Too long, didn't read. It's all about bonding and intermolecular forces, particularly electronegativity. So we're going to talk about different types of chemical bonds. And we're going to look at the relationship between the types of bonding and the properties of the elements participating in the bond. So the concept of electronegativity values for the representative elements, we know that increases electronegativity, the tendency of an electron, of an atom to pull electrons to itself, toward itself, preferentially. That tendency is going to increase going from left to right across a period, and it's going to decrease when you go down a group. So here is just a great way to visualize this. The least electronegative element is cesium. The most electronegative element is fluorine. Remember fluorine, and it will always tell you the trend. Notice we don't include the noble gases because they tend not to form compounds. Notice that as you get closer and closer to fluorine, the units known as the Pauling units, they have no value. That's just a relative attraction, get much, much larger. So 4 is the greatest, and cesium, francium are 0.7 the least. So these can help us qualitatively understand these various trends, the trends that we mentioned where electronegativity increases and right to left and decreases down a group. We can examine that by looking at the electronic structure of the atom, what we know about the shell model, and the application of Coulomb's law. Valence electrons shared between atoms of similar electronegativity constitute a nonpolar covalent bond. So for example, if you have a bond between carbon and hydrogen, it's effectively nonpolar, even though from the chart, right, you can see that carbon is 2.5 and hydrogen is 2.1. But the difference between those two is only 0.4, and it's simply not enough to cause polarity. So carbon is slightly more polar, but not enough to make a big difference. Here, according to this estimation of electronegativity, 0.35. Now, valence electrons shared between atoms of unequal electronegativity constitute a polar covalent bond. And so you'll see this with oxygen and hydrogen. And this will create a partial charge as the more electronegative element, oxygen, pulls the electrons in this covalent bond. They're shared, but they're not shared equally. So they're pulled preferentially towards oxygen, which gives oxygen a slightly negative charge, and it leaves a slightly positive charge on the hydrogen. And that leaves, in this case, a net charge on the molecule. This side of the oxygen molecule is slightly negatively charged, and these hydrogens on this other side of the oxygen molecule are positively charged. And so you have a polar molecule. You can have polar bonds, polar bonds, but they can cancel each other out, as in the example of carbon dioxide. Here you have between the oxygen and the carbon a slight negative and a slight positive, but these slight negatives on these oxygens end up canceling each other out, so there's no net, what they call net dipole moment, no net vector of electrical force, but you can see you do have it here, the net vector. So basically, at the end of the day, do you have a positive side of the molecule and a negative side of the molecule? If it's both positive, positive, or negative, negative, they cancel each other out, and it's effectively nonpolar. So as we mentioned, the atom with higher electronegativity will develop a partial negative charge, and at some point, right, we move from covalent. So covalent is generally considered to be an electronegativity difference between 0 and 0.4. Above 0.4, we consider that to be slightly polar, so polar covalent. And that continues up to, different charts have different numbers, but between about 1.7 and 1.8, this chart has their cutoff at 2.0. But somewhere as we approach 2, it becomes predominantly ionic in character, and not just polar covalent. And the interesting thing to notice here is that this is a scale. These are not degree differences of kind, but differences of degree. So here's equal sharing, slightly unequal sharing, so unequal that now the electrons have effectively been transferred or stolen by the more electronegative element and forming, in this case, an ionic bond rather than a polar covalent bond. In single bonds, greater differences in electronegativity will lead to greater bond dipoles, and that's just the amount of difference between the positive and the negative side. So again, there's a scale between pure covalent, which starts at a 0 difference. Anything less than about 4 is considered pure covalent. Anything between 4 and 1.8 is considered polar covalent. Anything above about 1.8 is considered ionic. Again, different charts will vary, but that's a pretty good rule of thumb. Remember, all polar bonds have some ionic character, and the difference between an ionic and covalent bond is not distinct. It's rather a continuum, and even that point is rather arbitrary. Is it 1.7, 1.8, 2.0? That's a rather arbitrary cutoff, where you're moving from a less and less polar character, polar covalent character, and more ionic character. So this is just showing the increasing ionic character as you move from a low difference in electronegativity to a high difference in electronegativity. Again, so you can see this chart says 0.5 to 1.7. Again, so just somewhere around 0.4 to about 1.8 is your breakdowns. Don't get too hung up on the exact number. The difference in electronegativity is not the only factor in determining if a bond is designated ionic or covalent. Now, because we know that generally if we're dealing with a bond between a metal and a non-metal, that's going to typically be ionic, whereas bonds between two non-metals are typically going to be covalent, even if the electronegativity difference falls within that threshold that we mentioned earlier. So how do we determine it? We look at the properties of the compound, and that's the best way to characterize the type of bonding that we have. All right, our next topic is intermolecular force and potential energy. And this allows us to graphically represent the potential energy as it relates to the distance between the atoms. So this will help us describe this interaction. And here's a very useful chart or graph, I guess, or whatever this is, this picture. So here we're looking at the internuclear distance in picometers. And what we can see here is when their radii are about 300 pm apart, there's very little attraction. But as they move closer and closer together, the attraction grows, and the potential energy, that's the energy that's released as these atoms come together. So imagine a ball rolling down a hill, right? It's got higher potential energy here. As it rolls down the hill, it releases that potential energy as kinetic energy. And that's just for your physics folks. If that doesn't make any sense, just forget about it. But that there's energy released as these two atoms slam together or get closer and closer together, up to a point. This is the Goldilocks point. After this point, where they have their shortest bond distance, well, the shortest bond distance that's stable, if you push them closer and closer together, that's going to result in that you have to add energy to do that. Why? Because you're pushing these nuclei, positively charged nuclei together, and the repulsive forces are going to begin to overwhelm the attractive forces. So here, attractive forces predominate until you get to the Goldilocks sweet spot, and then the repulsive forces take over if you try to push those atoms too close together. So it illustrates the equilibrium that we get, the bond length that we get where the atom is in equilibrium, where it's as close as it can be, but not so close that it starts to experience repulsion. So it's maximizing attractive forces, minimizing repulsive forces. And at that point, its potential energy is at its lowest. And remember, things at their lowest energy potential are like if I rolled a bowling ball down this hill, right? It's going to want to sit right here at the lowest point. That's where it's the most stable. Things are most stable at the lowest energy level. So that's where we're going to see the potential energy is the lowest, and the bond energy that required to separate them is going to be the highest. So here's another just description here. The potential energy decreases with increasing orbital overlap. We get the balance. This is the equilibrium point, and then here repulsive forces take over. So in a covalent bond, the bond length is influenced both by the size of the atom's core and the bond order, whether it's a single bond, a double bond, or a triple bond. And as you're going to see, single bonds are longer, double bonds are shorter, triple bonds are shorter yet, because they are pulling, those extra bonds are pulling the atoms closer and closer together. So that's going to be influenced by the size, the size of the atoms that are trying to get close together. Right? Bigger atoms aren't going to be able to get as close together before they begin to experience more repulsion. And things are going to be pulled together closer the more bonds that they experience. So another depiction of the same thing. So we can use Coulomb's law to understand the strength of interactions between the cations and the anions. Because the interaction strength is proportional to the charge on each ion, larger charges will lead to stronger interactions. Because the interaction strength increases as the distance between the center of the ions decreases. So the strength, as you get closer together, when you're talking about an ionic charge, the closer they can get together, the more attractive force they'll have. Smaller ions tend to have stronger interactions, stronger electrostatic attraction. So to summarize this part, as electrostatic charge goes up, so if we go from a +1 ion to a +2 ion, the force will go up. As distance goes down, they're going to get closer to the attractive force is going to go up. As bond length goes down, same thing, attractive force is going to go up. As size goes down, right? That would be the same as reduced distance. As size goes down, they're going to get closer together, and you're going to have stronger Coulombic attraction. That takes us to the structure of ionic solids. This is just regular Gen Chem stuff, but we're going to just apply Coulomb's law to the properties of the ions. We know that ions form a giant crystalline lattice, an array. It's not just one chloride hanging out with one sodium. They arrange themselves in this systematic 3D lattice that maximizes attractive forces among the cations and anions and minimizes repulsive forces. So you can see if you pick any one atom here, it's surrounding itself as closely as it can with these oppositely charged number ones, and as far as it can get from these same charged number twos. So when everything is sitting here fat and happy, these bonds are very, very strong. But it only takes a slight bit of movement, a slight bit of stress. If we can shift this 2, for example, over one space, one atom, then all of a sudden, instead of being attracted to this 1, it's going to be sitting over this 2. And now all of these 1s are going to be lining up, and all these 2s are going to be lining up, and they're going to experience this repulsion. And that is a stress fracture or a cleavage plane. So that's why ionic compounds tend to be brittle, because if you stress them even a little bit and shift them, then they explode apart. They pop apart because, again, the attractive forces that were maximized now become repulsive forces. That takes us to the structure of metals and alloys. Again, this is just a refinement of our Gen Chem understanding. We want to look at how we represent a metallic solid and our alloy to explain some of the essential characteristics. So when we look at a metal solid, it's helpful to consider it as all the metal ions. Think of these are the protons, right? Surrounded by these valence electrons. But these valence electrons, instead of being locked in a rigid arrangement like this ionic compound, these electrons are free to move. They're free agents. So we talk about there being a sea of valence electrons that can, and these electrons can shift and move, which makes metals such great conductors of electricity. Their negative charges on the valence electrons are not locked down in a rigid crystalline network, so they're free to move and conduct electricity. And again, here's a group 1 metal with a +1 charge, if you will, because it has a -1 valence electron. Here's 2 negative charge valence electrons, so an effective +2 ion. And again, we consider this to be as an ion. It's not really an ion, but we consider it to be like an ion surrounded by a delocalized cloud or sea of valence electrons. Now, what about alloys? Alloys are when you have atoms, different atoms that combine in different ways. And we're going to see 2 different kinds of alloys, interstitial alloys and substitutional alloys. And the first of these, the interstitial, they form between atoms of different radii, so different sizes. And what happens is if you have a big enough atom in a metallic solid, there's space in between them, which is called the interstitial spaces, for a smaller atom to squeeze in there. So, for example, carbon can squeeze in into the spaces in iron, and it makes the alloy known as steel. So this is an interstitial alloy. This would be a representation, for example, of an iron ion, right? And this would be considered this is a carbon, and this carbon can fit in this space, in these spaces, these interstitial spaces. This creates an interstitial alloy. This is different from a substitutional alloy. These form between atoms of around the same size radii. So they're too big to fit within their spaces, but one atom can substitute or replace another in the lattice, as it were, in the solid. And so here's what you have in a substitution alloy. You have some of the original, whatever it is, might be gold being replaced by silver, it might be copper being replaced by some zinc, but you replace certain atoms with others of roughly the same size. This is different from interstitial, where the original atoms all stick around. We're just sticking some interstitial smaller atoms in these spaces between. So here's an example of a substitutional alloy. When you have 14 karat gold, you replaced about half of the gold atoms with silver. Here's an interstitial alloy known as steel, which we already mentioned, carbon stuck into the interstitial spaces with the iron. Now it takes us to Lewis diagrams. And we're going to learn to represent a molecule with a Lewis diagram. And then we're going to use what's known as valence shell electron pair repulsion, or VSEPR theory, to explain the orientation of these electron pairs in three-dimensional space. So first, a Lewis structure represents the chemical bonds and valence shell electrons in a molecule. So here's how we represent water. We start with water. Water has oxygen has 6 valence electrons. We're going to take care of 2 of those with this covalent bond here. Sorry, one in this covalent bond. So hydrogen is going to contribute an electron. Oxygen is going to contribute an electron. That's what this is. So every bond is considered a covalent bond, a sharing of 2 electrons. Same here. So now we have oxygen with an octet, which is what it wants. Hydrogen with a duet, which is what it wants. Here's how we would represent nitrate. Okay, nitrogen is the central atom, and it has a single bond to each of the oxygens and a double bond to the remaining oxygen. And as we're going to see, this is capable of being represented in multiple ways, and so it's going to have what we call resonance structure. We'll get to that in a second. Here's carbon dioxide. Again, we start with the 4 valence electrons of carbon. We start passing them around to make the bonds. until everybody has their octet and everybody's happy. So here's the basic thing. You find the total number of valence electrons, you draw a skeleton using single bonds, you assign the remaining the remaining valence electrons usually to the more electronegative chemicals atoms first, and then you make multiple bonds if the octets are not fulfilled. And then if there's a charge, this is important, if there's a charge on the overall molecule, you put brackets around it and then you indicate the charge. If you don't bracket it and indicate the charge, you're going to get it wrong. So again, another way to show drawing the Lewis dot structure for NO3, and as we're going to see, it's capable of being represented in three different oxygen configurations, with the oxygen doubled up on the top one, on the one over to the right, and one over to the left. And that means that they're all possible, in which case they're all, the actual structure is going to be a mix of all three. Okay, so that takes us to resonance, which we're going to talk about, and formal charge. So where we can draw more than one Lewis structure, we have to include this notion of resonance to refine that structure. So as we mentioned, there's more than one correct Lewis structure that we can draw for our nitrate. We can double here, double here, double here, and the actual structure is actually a hybrid, or the average of all three of those. We need this refinement because we can look at the bond length. Remember I said that single bonds are longer than double bonds. So if this were the actual, if just this one were the actual, then we should find two longer bonds and one shorter bond to the oxygen. But when we examine it experimentally, we find that all three bonds, the bonds between nitrogen and all three of the oxygens, are equivalent. So that means that we don't have this, oh, it's always on the left, or it's always on the bottom, or it's always on the right. Essentially, it's a hybrid of all three. So that's why we need resonance to account for the experimental value that there is no difference in the strength and length of these three oxygen bonds. So basically, we're always going to use the octet rule, and we're going to use formal charges to find out which of several possible Lewis diagrams provide the best model for predicting molecular structure and properties. Remember, the octet rule is that atoms gain or lose or share electrons to fill their outermost energy shell with 8 valence electrons. So here, oxygen and carbon form a double bond. They share 4, so that carbon gets credit for 8, oxygen gets credit for 8, everybody's happy. Now, the concept of formal charge, which helps us to decide between the likelihood or unlikelihood of certain Lewis diagrams, basically just means when we're looking to find the formal charge, we're looking to see, we're going to start with the number of valence electrons that the neutral atom starts with. So in this case, let's look at this. This is nitrogen, and it starts with 5. And then we're going to subtract all of the electrons that are assigned to it. And that means any unshared electrons, what we call lone pairs, and half of any shared electrons that we're going to see in these covalent bonds. So in this case, we're going to see that the formal charge, we're going to start with the 5 electrons that nitrogen starts with. We're going to subtract the 4 electrons in these 2 lone pairs. And then we're going to give nitrogen credit for 2 of the 4 electrons in these covalent bonds and subtract that. So it's 5 minus 4 minus 2. That gives us a formal charge of -1. Okay, and that's consistent because we know that this molecule as a whole has a -1. So you actually could assign the negative charge in this case to the nitrogen. But it's safer just to bracket the whole thing and throw it on the outside. So again, how do you find formal charge? Count the electrons. So, you start with valence electrons, you subtract the electrons assigned, and that gives you the formal charge. And that allows you, for example, to distinguish, because both of these are possible Lewis diagrams for CO2. You could have two double bonds, or you could have a single bond and a triple bond. And everything still has an octet, right? Carbon is happy, has an octet. This oxygen has an octet. This oxygen has an octet. So which of these two structures should we prefer? Well, the one with the lowest formal charges. Lower formal charges are associated with greater stability, which means greater probability that that's how you're going to find this molecule in the wild. You do your formal charge calculations, you find that this is 6 minus 6, 4 minus 4, 6 minus 6. So all the formal charges are 0, 0, 0. Whereas over here, you get 6 minus these 6 plus half of that, so that's 6 minus 7. This has a negative 1 charge. And this is fine, has a 0, but this has a positive 1 charge. So while both can technically satisfy the Lewis octet structure rules, this is not. This is much more unlikely to have a molecule with a positive charge on one side and a negative charge on the other, vice versa, when you could just rearrange it to have no formal charges. So bottom line, if you can find a Lewis structure that has lower formal charges, then that's to be preferred. As with any model, there are limitations, like a lawyer, with the use of the Lewis structure model, particularly when you deal with odd numbers of valence electrons. So here is an example of an odd number of valence electrons, ClO2, where we have this lone electron here. Where are you going to put it? So, and if you put it on an oxygen, which oxygen? So you're typically going to leave it here with the central atom. And while this is not associated with stability, these do exist. You do have odd numbers of valence electrons sometimes. Those are often called free radicals because they're very reactive with other things. Okay, that takes us to VSEPR and bond hybridization. So we're going to explain the structural properties of molecules and the electron properties of molecules using this very powerful notion. I call it just balloon theory, right? Valence shell electron pair. So electron pairs in a valence shell are going to repulse each other. They want to get as far as they possibly can from each other. So if you have two bonds with electrons, or two sets of lone pairs, doesn't matter, they're going to want to orient themselves on the molecule as far as from each other as possible. So if you have two pairs around a molecule, they're not going to both be clustered up here together. They're going to orient themselves on opposite sides or opposite poles, right, of the atom, and they're going to get 180 degrees apart. So again, you can just do this with balloons. If you tie two balloons together, they're going to orient themselves 180 degrees. If you tie three balloons together, they're going to orient themselves 120 degrees apart. If you get four balloons, they're going to orient themselves like a tetrahedron, 109 degrees apart. So on with 5 balloons and 6 balloons and so on. So this lets us predict the shape of a molecule based on the electron configurations of the constituent atoms. And basically, the atoms are going to get as far apart as they possibly can to prevent any crowding. So this is an application of Coulombic repulsion as a way to predict the arrangement of electron pairs around a central atom. And so you're going to see these diagrams, and these are worth memorizing. You need to remember that if you have a central atom with two atoms bonded to it, they're going to assume a linear shape. If there's three, or if you have three and an electron pair, that electron pair is going to, again, get as far away from the electrons in this bond and in this covalent bond as it possibly can. So even though there isn't an atom here, these are going to try to get as far away from each other as possible, and they will assume this planar shape. But when we look at the geometry of the molecule, we're going to not look at this lone pair, and we're going to say, if we just look at the atoms, this is going to look bent. But it arranged itself like a trigonal planar, and then we just ignore this part when we look at the geometry of the atom. So we're going to distinguish between what's known as the electron geometry, which is going to take into account all the electrons, including the non-bonding pairs, and what we call atomic or molecular geometry, which is just going to look at the arrangement of the atoms in the molecule. So in this case, since you have 3 atoms around a central atom, this will be trigonal planar. But if you replace one of these with a lone pair, then you would basically wipe out. Oh, here we have to start with a tetrahedron, and then we would wipe out our tetrahedron and be left with a trigonal pyramidal or a squashed pyramid. So same thing happens when you start with these other geometries and you begin to replace them with lone pairs. Again, it's important to distinguish. Are we talking about the geometry of all the electron domains? That's known as the electron geometry. Or are we talking about the geometry of the atoms surrounding the central atom? We call that molecular geometry. So remember, the electron geometry is always going to be fixed. So if it's 2, it's linear. If it's 3, it's trigonal planar. If it's 4, it's tetrahedral. If it's 5, it's bipyramidal. If it's 6, it's octahedral. That never changes. But the molecular geometry, if we replace one of those elements with a lone pair, so in this case, here's one where all 3 are atoms, but here we just have 2 are atoms, and this other one is an electron pair. Okay, it's still going to assume the same basic trigonal planar shape, but when we look at the arrangement of the molecules themselves, this becomes bent. So again, you're going to have to memorize the electron geometry, which doesn't change, and then from that start subtracting the lone pairs out to see what you have left. It's probably worth remembering some of these basic bond angles. 180 between 2, 120 between 3, 109.5 on a tetrahedron. That's a very, very common angle. You'll need to know that for sure. And so here is a great chart. Again, it gives you the electron geometry, which is always going to be the same depending on the number of bonding and non-bonding electrons. So if you have 5 electron groups, doesn't matter how many are in bonding, how many are bonded and unbonded, all 5s are going to be trigonal bipyramidal. Right? Look at all the 5s. The electron geometry is always going to be trigonal bipyramidal. But depending on how many of those have been replaced by electron pairs, you're going to get different molecular geometry. It might be, if all 5, it would be the same. So when you don't have any electron pairs, the molecular geometry is the same as the electron geometry. But if you start replacing them, then your trigonal bipyramidal. If you replace 1, it becomes a seesaw. If you replace 2, it becomes a T-shape. If you replace 3, okay, it becomes just a good old-fashioned linear. All right, so you're going to see that it's worth committing all of these electron geometries to memory because they're going to be the same. They don't change. And then begin to practice with subtracting. Right? So if you start with a trigonal planar and you subtract out the top, then you're left with a bent molecule. If you start with a tetrahedron and you subtract out one of these, you're left with a squashed pyramid, which is what we call trigonal pyramidal. If you subtract 2 from a tetrahedron, you're just left with a bent molecule. Okay, so just go through these and know the difference between electron geometry and molecular geometry. And it's helpful sometimes to know these approximate bond angles. You can get these just by, if you're good at visualizing, you can get them or bring balloons or anyway, just know the basic bond angles, know the difference between electron geometry and molecular geometry. Okay, so this allows us to predict a ton of structural properties of molecules, including molecular geometry, bond angle, relative bond energies based on bond order, right? Whether it's a first or a second or a third, whether it's a single bond, double bond, triple bond. Relative bond lengths, the presence of a dipole, which is an electric charge, a net electric charge on the molecule. Hybridization of the valence orbitals of the molecule. So you'll often see the terms hybridization or hybrid atomic orbital to describe the arrangement of electrons around a central atom. And basically, if there's 2 bonds, it's going to be sp. If If there's 3 bonds, it's going to be sp2, and the bond angles are going to assume that trigonal planar 120 degrees apart shape. sp3 is 4 bond angles, and that's going to assume our typical tetrahedron shape. So the way to remember this is just go count how many bonds we have here. S's can form 1 bond, they have 1 pair of electrons. P's can form up to 3 bonds because they have 3 subshells. And if you need more than that, start tacking on D's. So an sp3 is 4 bonds. sp is 2 bonds. sp2, 3 bonds. If I needed 6 bonds, that would be an sp3 and a d2. All right, so that is your breakdown here. So just count these out. sp, that's 2. sp2, that's 3. sp3, that's 4. sp3d, that's 5, and so on. Again, great visualization here of your bond angles that you get. Again, another way to do this, if you really care about how the s orbital and the p orbitals orient themselves, here you have 1 s and 1 p, here you have 1 s and 2 p, here you have 1 s and 3 p. At the end of the day, just remember, add your s's, your p's, and your d's, and that gives you the total bonding electron pairs and lone pairs around the central atom. Okay, now bond formation happens because there is overlap between the atomic orbitals. That's how they share electrons in covalent bonds. In multiple bonds, this overlap leads to the formation of both sigma and pi bonds. Now be careful here. When we talk about sigma and pi bonds, we're not talking about this kind of orbital hybridization. That's talking just about the orientation of the electrons around a central atom. That's just the electron domains around one atom. Here we're talking about single bonds, double bonds, triple bonds formed between 2 atoms. So when you see sigma and pi, don't think S and P3 hybridization. All right, that they're 2 different concepts that unfortunately seem very similar. All right, here's how we look at a pi bond. So the first bond, a single bond that forms, is going to be known as a sigma bond, and that's a very strong bond. It's stronger than the pi bond. The pi bond is going to be formed by these p's overlapping each other, and so remember we're talking about all the electron domains here. Carbon has a couple of electronic domains, and so here's one set of here's one bond, and then these are able to form a second bond called a pi bond, and it makes a kind of a weird shape. This overlap is stronger in sigma than pi, and we see that because sigma bonds have greater bond energy to break them than pi bonds. But here's the breakdown. Here's what you need to know about sigma and pi bonds. If you're dealing with a single bond between atoms, it's a sigma bond. If it's a double bond, it's 1 sigma and 1 pi. And if it's a triple bond, it's 1 sigma and 2 pi bonds. Here's a kind of a visualization. The pi bonds, they bond above and below the sigma bond, and that creates something called, it prevents rotation. Sigma bonds can rotate without freely, but pi bonds, they add an extra layer of rigidity, and it doesn't allow rotation. Triple bonds are going to be made up of 1 sigma bond and 2 pi bonds that look like 4 hot dogs clustered around the pi bond or the sigma bond. Again, you don't have to know anything to think about those shapes, but just realize that if you're dealing with a triple bond, it's a sigma and 2 pi, whereas a double bond is going to be a sigma and 1 pi. Here is just a way, again, of trying to visualize the double overlap here. This one caused by the sigma, and now here we're talking about sp2, but we're talking about these are the 3 orientations around this carbon atom. All right, so I know this gets a little confusing because you have all these S's and these P's. Sometimes we're talking about the electrons around a single atom, but then we're talking about how they combine to form sigma and pi bonds. They are different concepts. You have to recognize that. Right? Orbital hybridization is simply what the electrons around a single atom. Sigma and pi bonds, or sigma and 2 pi bonds. Now we're talking about covalent bonds between atoms. So bottom line, single bond, 1 sigma, double bond, a sigma and a pi, triple bond, 1 sigma and 2 pi. So if someone asks how many sigma and pi bonds are in this molecule, acetic acid, you're going to say, okay, you got sigma, 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 sigma. Those are all the single bonds. They're always going to be sigma. And you have 1 double bond, which is a sigma and a pi. So if you were counting them all out, you'd say there are 7 sigma bonds and 1 pi bond that is found here in this double bond. Remember I said the pi bond prevents rotation and gives us what's called structural isomers. So this can no longer rotate freely, so you can sometimes have a molecule where both of these are up on the same side, or one's up, one's down. And so this gives you cis and trans versions. You don't have to know this, it's organic chemistry stuff. But just realize these will not allow rotation. So this can't flip around and become this, and vice versa. All right, key concepts. Hugely important to know the effects of electronegativity difference on bond type, right? Low electronegativity difference, covalent bonds, nonpolar covalent. Medium electronegativity difference, polar covalent. High electronegativity difference, ionic bonds. We can create ionic solids when we have ionic bonds. They create these giant crystalline networks that maximize attraction and minimize repulsion. This is different from metallic solids, which are basically a network or a lattice of positive ions surrounded by a delocalized sea of negative electrons, the negative valence electrons. This makes solids much more malleable. You can hammer them and deform them, and they don't shatter the same way ionic compounds do. All right, we talked about how to form Lewis diagrams. Just follow your duet and octet rules, but use formal charges to decide between valid Lewis diagrams. VSEPR or balloon theory will help you predict the geometry of both the electrons, and the electron domain geometry, as well as the molecular geometry, the geometry of the individual atoms, when we don't consider the unbonded pairs. If things can be drawn more than one way, that gives rise to resonance, which is a way of explaining the experimental data. The octet rule obviously is everything likes to get 8, unless it's small, like hydrogen, in which case it's happy with 2. We talk about bond hybridization, which is how we distinguish a single bond from a double bond from a triple bond. All right, that's it. Thanks for your time.